You've been told the speed of light is the fastest anything can move, but you were never told why the universe needs that limit, because this isn't about light being fast. It's about what happens to space, time, and causality itself when anything tries to go faster. At that boundary, clocks slow, distances vanish, events stop agreeing on what came first. Imagine a message arriving before you even hit send, a universe where an effect shows up with no cause behind it. That's the price hidden inside faster than light. Tonight, you'll understand why light speed isn't just an ultimate limit, it's a limit reality is built to protect. Before we explore that limit, if you find value in these deep space videos, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. For most of human history, the universe didn't feel like it had rules written into its bones. It felt like a wide, indifferent place, where motion was simply motion, and time was simply time. When we watched a stone fall, we didn't think, there is a limit to what reality allows. We thought, this is how things behave. And that was enough. We lived inside a world that seemed honest, a world where distances could be crossed if only we were strong enough, patient enough, clever enough. A world where speed was not sacred, just effort, just will. And if something moved faster, it was only because something pushed harder. But that quiet assumption hid a dangerous idea. It meant there was no final boundary, no ultimate edge, no speed that reality would refuse. It meant the universe had no fence. And that's where the story begins, not with light, not with stars, but with the ancient human mind, trying to make sense of motion, without ever suspecting that motion might have a ceiling. Imagine this. We're standing on an empty road at night. No streetlights, no engines, no screens, only darkness and the sound of our own breathing. In the distance, a friend raises a torch. We count the steps between us. We measure the time it takes to walk that distance. We can understand that. But when the torch ignites, the light doesn't feel like it travels. It doesn't arrive like a thrown stone or an arrow or a shout. It simply appears. The world around us is suddenly visible, instantly, as if the universe doesn't need time to deliver brightness. For an ancient observer, that feeling wasn't childish. It was reasonable, because in daily life, light doesn't behave like a moving object. It behaves like a condition, like an opening, like a curtain being pulled away. And so, for a long time, humanity didn't ask how fast light moved. We didn't even know what it would mean to ask. In the ancient world, motion was studied with the tools available to the human body. Eyes, hands, ears, the slow rhythm of walking, the quick violence of a thrown spear, the steady pull of an ox cart, and everything we could physically experience whispered the same message. Speed can always be increased. A horse can outrun a person. A falcon can outrun a horse. A stone can fall faster than any animal can run. So the mind forms a simple ladder. Slow, faster, faster still. No end required. This is why the idea of a cosmic speed limit wasn't just unknown, it was unnecessary. Because a limit implies a universe that says no, even when we say more. And in the ancient imagination, nature didn't speak that way. Nature wasn't a strict judge. Nature was a pattern. To build any science, we need a stage. We need a place where events happen, and a clock that keeps order. For centuries, that stage was simple. Space was like an endless room. Time was like an endless river. They weren't connected. They weren't negotiable. They didn't bend. They didn't argue with matter. Space was where things existed. Time was what happened to them. And because space and time were treated as separate, motion became something almost mechanical. If you knew where something was and how fast it moved, you could imagine where it would be later. It was a comforting worldview, It told us the universe was understandable in the same way a road is understandable, in the same way a straight hallway is understandable. You start here, you walk there. Time passes in the same way for everyone, and nothing about light threatened that picture, because light, to human senses, didn't feel like a traveller. It felt like the arrival of knowledge. Now we reach one of the most natural assumptions the human brain ever made. If you walk forward on a moving cart, you go faster than the cart alone. If you throw a stone from a running horse, the stone inherits the horse's motion. Everything in daily experience teaches us this. Motion stacks, speeds add. There is no penalty for combining them. It's as simple as carrying a cup of water while walking. The water doesn't care about the ground beneath you. It comes along for the ride. So the old logic seems unavoidable. If we can move fast, and then we launch something from that fast-moving platform, it must go faster still. There is no hint of an upper ceiling, no whisper of a maximum, only arithmetic, only accumulation. And for ordinary life, that logic works. But it quietly builds a universe where faster and faster is always possible, and where nothing in nature has the authority to stop it. Here is the strange part. Our senses are magnificent, but they are not built for cosmic truth. Our eyes can't track the motion of light. Our brains can't feel the difference between instant and almost instant. Even the fastest things we witness, lightning, sparks, reflections, still arrive too quickly for the nervous system to separate into moments. So for most of history, we lived in an illusion without knowing it. We thought we were seeing reality directly, but we were seeing reality filtered through biological limits. We could hear echoes because sound is slow enough to reveal itself. We could watch birds cross the sky because their motion is slow enough to follow. But light was too fast to be experienced as travel. To us, it was not a moving thing. It was the immediate fact of visibility. And this matters, because if you cannot perceive something as motion, you don't naturally ask about its speed. And if you don't ask, you don't discover the rules hiding underneath. We need to understand what this worldview gave us. It gave us certainty. It told us time was the same everywhere, an invisible drumbeat ticking identically across the world. It told us space was the same everywhere, a rigid container that never changed its mind. It told us motion was straightforward. An object moves because something pushes it, and so the cosmos felt like a grand, silent machine, not a living geometry, not a delicate structure, just a stage, just a clock, just objects moving through emptiness. In that universe, a speed limit would feel like a betrayal, because a speed limit means there is a hidden structure to reality, a boundary that exists even if we don't want it to. A speed limit would mean the universe is not merely a place, it is a law. So why didn't ancient and classical thinking demand a universal maximum? Because the universe, as they understood it, had no reason to enforce one. To need a speed limit, we must first suspect that space and time are tied together in a way we can't see. The order of cause and effect is fragile. Information itself might have a maximum rate of travel, but none of that was obvious. In everyday experience, cause and effect are secure. We strike a drum, then we hear the sound. We shout across a canyon, then the echo returns. Everything happens in sequence with no paradoxes, no fractures. So it didn't occur to us that if something traveled too fast, the universe might break its own logic. The need for a speed limit is not intuitive. It's born from contradiction, and for centuries the contradictions hadn't arrived yet. This is what we must sit with. Humanity built vast philosophies of nature, without ever suspecting that speed could be a fundamental property of reality, not a technical detail, not an engineering challenge, a structural law. That gap wasn't a failure of intelligence, it was a consequence of our scale. We are small creatures living at slow speeds, inside a gentle gravitational field, on a quiet planet. Our daily world does not reveal extreme truth. It hides it. It hides it the way fog hides a coastline. The coastline is still there, sharp, real, unforgiving. But from where we stand, it looks smooth, it looks endless, it looks safe. And that is why classical physics, before the deep revolutions, could feel complete. Because the universe at human scale politely pretends that there is no speed limit. But then, a new kind of question begins to poison the old certainty. Not a philosophical question, a measurable one. A question that doesn't care what we feel. A question that doesn't care what we expect. A question that can be tested. It begins as a whisper in the background of science. If light isn't just an instant condition, if it is something that travels, then what is it doing between the torch and our eyes? And if it travels, does its speed change when we move? Does it behave like everything else we've ever thrown, pushed, rolled, or fired? Or is it something fundamentally different? Something that refuses the old rules? Because if light refuses, then the universe is not the simple stage we believed in. It is something stranger, something more severe, something with boundaries written into its design. And once we ask that question seriously, everything we thought was solid begins to tremble. For centuries, our picture of motion felt complete. If we move toward a sound, it reaches us sooner. If we chase a wagon, it feels slower to catch. If we throw a stone while running, it carries our running into the throw. That's how our world behaves. So when we finally began to suspect that light might travel, we carried the same assumption into it without even noticing. We expected light to behave like a stone. We expected its speed to stack, to add, to change with us. But then the universe offered a result so clean, so cold, it felt almost insulting. Light refused, no matter how we moved, no matter how we chased it, no matter how we tried to catch it with our own motion. Its speed didn't behave like the rest of reality. And once we saw that, the classical world didn't just wobble, it began to fracture. To measure the speed of light, we first had to accept something uncomfortable. Light might not be instantaneous. That sounds simple now. But for most of history it wasn't. Because to a human nervous system, light is effectively immediate. It arrives too fast for our senses to separate then from now. So the first challenge wasn't building an instrument. The first challenge was building doubt. We needed a situation so vast, so large in distance, that even light would be forced to reveal a delay. And Earth is usually too small for that trick. Even across an entire city, light's travel time is a whisper. It's there before the mind can register before. So we had to go bigger. We had to use the solar system itself as our laboratory. In the 1700s, and even before, astronomers were already obsessed with timing. They weren't timing light. They were timing orbits. They watched moons slide behind planets. They watched eclipses repeat with mechanical regularity. And one of the most important clocks in the sky was a moon named Io, one of Jupiter's moons. Here's where the story cracks open. An astronomer named Ola Ruma noticed something strange. The eclipses of Io didn't always appear exactly on schedule when seen from Earth. Sometimes the eclipse seemed late, sometimes it seemed early. At first, that kind of inconsistency looks like a messy measurement problem, but then the pattern revealed itself. When Earth was moving away from Jupiter, the eclipses seemed to drift later and later. When Earth was moving toward Jupiter, they drifted earlier. It was as if the message, the light carrying the event, was taking longer when the distance grew. Not because Jupiter changed, not because Io changed, because the space between us changed. That was the first real wound in the old assumption of instant light, a quiet admission carved into the timing of the heavens. Light takes time, and if light takes time, then it has a speed. Over the next centuries, scientists refined that speed again and again. They built experiments on Earth, clever, delicate, unforgiving. They used spinning mirrors, rotating wheels, long corridors, precise timing. Names like Hippolyte Fizeau, Léon Foucault, and later Albert Michelson became part of a long, obsessive effort, not to guess how fast light moves, but to measure it until the universe could no longer hide behind uncertainty. And the number they converged on is staggering. Light moves at about 300,000 kilometers per second, about 186,000 miles per second. Those words can pass through us without meaning, so we have to translate them into something the body can feel. At that speed, light could circle Earth more than 7 times in a single second. In the time it takes us to blink, light could lap the planet again and again. From New York to Los Angeles, about 2,450 miles, around 3,940 kilometers, light would cross it in about 1/100th of a second. It doesn't feel like motion, it feels like a violation. And yet, that was only the beginning, because measuring the speed of light is not what shattered classical physics. What shattered it was what happened when we asked the next, obvious question. If light has a speed, then our motion should affect it. That's what everything else does. If we run forward and throw a ball, someone standing still sees the ball moving faster than if we had thrown it while standing. So we expect the same with light. If we chase a beam of light, we should measure it as slower than someone who stands still. And if we race toward a beam, we should measure it as faster. That's not philosophy, that's everyday reality. So the classical mind tried to protect itself with one last invention: a medium, a substance, a hidden ocean filling all space. They called it the luminiferous ether. The idea was seductive. If light is a wave, then like sound waves in air, it might need something to wave through. And if that ether existed, then Earth moving through it should create an ether wind. Just like sticking your hand out of a moving car window, the air rushes past. So the ether should rush past too. And that would mean one direction of light should be measured as slightly faster, and the perpendicular direction slightly slower, depending on how we move through the ether. A simple prediction, clear, testable, and terrifying. Because if the ether wind existed, the speed of light would not be the same in every direction. It would depend on motion, on our motion, on Earth's motion, on the observer, which is exactly what classical physics expected. So scientists built the test. They built it with the seriousness of a trial. Imagine this. We're in a quiet room, the air still, the floor heavy beneath us. In the center is a device so sensitive it feels almost alive. Mirrors arranged to split a beam of light into 2 paths at right angles. One beam goes one way, one beam goes the other. Then they return and recombine. If one beam takes even a slightly different amount of time than the other, the recombined light creates a shift, a pattern that moves like a fingerprint sliding. It's a trap for reality, a trap that catches tiny differences no human sense could ever detect directly. This is what Albert Michelson and Edward Morley built in the 1800s, and the logic was brutal. If Earth moves through an ether wind, then as the apparatus rotates, the light moving with the wind should behave differently than the light moving against it. The interference pattern should shift, not by much, but enough. Enough to prove the ether was real, enough to preserve the old world, enough to keep space and time absolute. So they ran the experiment, they rotated the apparatus, they watched, they waited for the universe to confess. And then, nothing. No shift, no wind, no directional change. Light did not care how Earth moved. It did not care how the instrument turned. It did not care how the observer traveled. It behaved as if its speed was fixed, locked, immune to motion. It was a result so disturbing that at first it didn't feel like a discovery. It felt like a mistake. This should be impossible. If we're moving and light is moving, how can both of us agree on the same speed? In ordinary life, we can't. If 2 cars race down a highway, their speeds combine in obvious ways. So why doesn't it happen with light? Here's the strange part. This isn't just one experiment. Over time, other experiments tightened the net. They changed the lengths of the light paths. They compared different orientations. They tested different times of day, different seasons, different speeds of Earth in orbit. Again and again, the same answer returned. No matter what we did, we couldn't make light's speed change by changing the observer. That fact didn't just dent classical physics, it threatened the foundations. Because classical physics wasn't just a set of equations, it was a worldview built on a promise. Space and time are separate, absolute, and shared by all observers, and the speed of something, anything, should depend on how you move. But light was telling us that promise is broken. At first, scientists tried to patch the old story. They weren't foolish, they were careful, because when a theory works for centuries, you don't throw it away casually. So they searched for ways to keep the ether and keep classical space and time. Some proposed that maybe Earth drags the ether along with it, like a ship dragging water. But that idea collapses when compared against other observations. Others tried different kinds of ether, thicker, thinner, more complicated, less detectable. But complication is not explanation. It's camouflage. One of the most famous attempts to preserve the old framework came from George Fitzgerald and Hendrik Lorentz. They suggested something astonishing. Maybe objects physically shrink in the direction of motion through the ether, not because of stress or heat, but because motion itself causes contraction. That idea wasn't poetic, it was desperate, a way to rescue the ether by claiming that our measuring rods betray us when we move. And the terrifying thing is, this kind of patch actually can mimic the experimental result. It can hide the ether wind inside the distortion of our own instruments. But that only raises a deeper problem. If motion can physically change lengths, then space isn't a rigid stage. It's involved, it's participating. And once we admit that, we're already stepping out of the classical world. We're already admitting the universe is stranger than we thought. So the situation became unbearable. On one side, we had centuries of intuition. Speeds add, time is universal, space is independent. On the other side, we had experiments that refused to agree. And the experiments weren't subtle anymore. They were repeating, refining, closing escape routes. Every attempt to preserve the old picture made the universe look more haunted, more unnatural. And that's when a deeper truth began to rise. Light is not behaving like an object we can chase. It is behaving like a rule, like a boundary condition, like a limit that reality enforces, not because of our technology, but because of how space and time themselves are structured. That thought is quiet, but it's catastrophic, because if the speed of light is the same for all observers, then the observers cannot share the same space and time. Something has to give. Either the speed of light changes, or our idea of time changes. Either light obeys our intuition, or our intuition is the thing that's wrong. And here is where we have to slow down. Because this is not just a scientific twist, it's a psychological one. If you were to board a fast spacecraft, faster than anything in human history, and shine a flashlight forward, your instincts would tell you the light should pull away a little faster than normal, because you're adding your speed to it. That's how the world feels like it should work. But the universe doesn't negotiate. No matter how fast you go, you still measure that beam leaving at 300,000 kilometers per second, 186,000 miles per second. It is the same. And if that is true, then the universe is forcing a trade. It's taking something from our classical picture to pay for that constancy. And we can't avoid asking what it takes. There is something almost poetic about this refusal. Light is how the universe tells us anything. Every star we see, every galaxy, every nebula, every distant event, it arrives carried by light. And if light speed changed with every observer, then the universe would have no stable way to keep events ordered across different motions. Reality would become a disagreement, not a shared story. So the constancy of light is not a detail. It's a kind of discipline, a strict, silent enforcement of coherence. But it comes at a cost, because to keep light speed fixed for everyone, the universe must reshape the very things we thought were untouchable: distance, duration, simultaneity, the basic meaning of at the same time. That's when the real problem appeared. We can keep our old idea of space and time, or we can keep the experimental truth about light. But we cannot keep both. By the late 19th and early 20th century, physics found itself in a strange position. We could predict planets with astonishing accuracy. We could build machines, engines, and industry on the reliability of classical laws. The old framework worked beautifully, until it didn't. And when it didn't fail softly. It failed on a point so fundamental that it touched everything: how motion relates to time, how time relates to space, and how the universe prevents information from becoming unbounded chaos. The speed of light wasn't just measured, it was protected from our motion, protected from our attempts to outsmart it, protected as if reality had welded it into place. So the discovery wasn't merely, light is fast. The discovery was, light behaves like a constant written into the structure of the universe, and once we accept that, we are forced into a new question. If light speed is fixed, and our motion can't change it, then what does change? Because something must. Space, time, or the meaning of both. And the moment we follow that question honestly, we step into a universe where space and time no longer sit apart like strangers. They begin to bend toward each other. And the old world, absolute, independent, comfortable, can't survive the contact. Once we accept that light speed refuses to change, the universe gives us a choice, not a comfortable choice, a violent one. Either the speed of light is not truly constant, and our experiments are somehow lying to us, or something we thought was untouchable is the thing that's wrong, and there are only a few candidates: space, time, or the quiet assumption that everyone shares the same now, because if a light always leaves at the same speed, for every observer, then the universe is telling us something terrifying. There is a deeper rule underneath motion, a rule stronger than our intuition, a rule that forces space and time to bend, so that light can remain unbroken. This is where the story stops being about a number, and becomes about the architecture of reality. Picture this: we're sitting in a car at night, parked at a red light. A second car is beside us. The road is still. The world feels stable. Now imagine that second car suddenly accelerates forward, faster and faster, until it becomes a streak of motion. Inside that moving car, someone turns on a flashlight and points it forward. Our instincts say something simple. They're already moving, so the light should leave faster. It should stack on top of their speed, the way a thrown ball stacks on top of a running arm. But the universe says no. From their seat, the beam still races away at the same cosmic number, about 300,000 kilometers per second, about 186,000 miles per second. And from our seat, watching them move away, the beam still races away at that same number. Both of us claim the same speed. This should collapse logic, because how can two observers, moving relative to each other, measure the same speed for the same beam? One of us must be wrong, except neither is. And that's when the old idea of space and time begins to fracture. Classical physics carries a silent belief, a belief so deep we rarely speak it aloud, that time is the same everywhere, that if we agree on what happened, we also agree on when it happened, that there is a universal present, one shared cosmic now, stretching across the universe like a flat sheet. So if two events happen at the same time for us, they happen at the same time for everyone. That belief feels obvious, but it was never proven. It was inherited from human experience, from a world where speeds are slow and distances are small. And the moment we demand that light speed stays constant, that belief becomes impossible to keep. Because if time were truly universal, then adding motion would change measured speeds, and light would behave like everything else. But it doesn't. So, the universe demands payment. To keep light speed fixed, it takes something away from us. It takes the idea of absolute time. This is where everything changes. The universe does not give every observer the same present. Two people moving relative to each other can disagree about whether two distant events happened at the same time. Not because they're confused, not because of flawed instruments, but because simultaneity itself is not a universal fact. It is a relationship, a consequence of motion, a fragile agreement that breaks at high speeds. That sounds abstract, so we have to make it physical. Imagine we're standing at the center of a long train platform. Two lightning bolts strike, one at the left end of the platform, one at the right end, at the same moment. We see the flashes arrive together, so for us they were simultaneous. Now imagine someone on a fast train passing through that platform at the exact center when the lightning strikes. They're moving toward one flash and away from the other, so the light from the forward strike reaches them sooner than the light from the backward strike. And because light speed is the same for everyone, they must conclude something disturbing. Those strikes were not simultaneous. One happened before the other. Same reality, same lightning, same universe, different time order. This isn't an optical trick. It's the only way the universe can keep light consistent. And once we accept that, we stop living in a world with a single shared now. We step into a world where time depends on motion. At the beginning of the 20th century, physics was carrying a contradiction like a wound. Experiments insisted the speed of light was constant. Classical space and time insisted it could not be. Something had to break. And in 1905, Albert Einstein did something simple and monstrous. He stopped trying to save the old assumptions. He treated the experimental truth as sacred, and he asked the only honest question left. If light speed is the same for everyone, what must be true about space and time? The answer wasn't a minor adjustment. It was a rewrite, a new foundation, a new kind of reality. Einstein's move was calm, almost quiet. He built special relativity on two ideas. First, the laws of physics work the same way for all observers moving at constant speed. Second, the speed of light in a vacuum is the same for all observers. Together, these ideas sound innocent, but they are not. They are a pressure that crushes the classical world, because if both are true, then space and time cannot be separate, absolute things. They must be flexible, they must adapt, they must change depending on motion, and the consequences are not optional, they are forced. Here's the strange part. When we move fast, time itself begins to behave differently. A clock in motion, relative to an observer, ticks more slowly. Not because it's broken, not because the mechanism struggles, because time itself is different along that moving path. This is called time dilation, but we have to resist treating it as a phrase. We have to feel it. A fast-moving astronaut does not merely seem to age less. In a real, measurable sense, their time between heartbeats is longer compared to someone at rest. Their processes unfold more slowly relative to us. And this isn't just theory. We've seen it. They've tested it with atomic clocks flown on airplanes. They've measured it in particles created in Earth's upper atmosphere, particles that should decay too quickly to reach the ground, and yet they arrive, because at their extreme speeds, their internal time runs differently relative to us. Time dilation is not poetry. It is experimentally real, a physical wound in the concept of universal time. And if you could ride alongside those near light speed particles, if you could somehow keep up with them, you would feel something subtle and terrifying. Your body would still feel normal. Your thoughts would still feel normal. Your heartbeat would still feel like your own. but the universe outside you would look different. Distances in your direction of motion would seem compressed. Clocks behind you would seem to race, not because reality is playing tricks on you, but because your motion has changed the geometry of time and space around your path. And you would realize we don't move through a passive stage, we move through a structure that responds. Time dilation is only half of the bargain. If time stretches for the moving observer, then something else must tighten. Otherwise, the speed of light wouldn't remain constant, so the universe does something even more unsettling. Lengths along the direction of motion become shorter, not in appearance, in measurement. A fast-moving object is physically contracted along its motion as seen by an observer. This is called length contraction. Again, not an illusion, not a perspective trick like a train shrinking into the distance. A real effect rooted in the same rules that keep light constant. This means space itself is not rigid. It has a kind of elastic obedience. And when we push motion toward the cosmic limit, space yields. We need to slow down here, because the mind tries to escape. It tries to say, this is just how things look. But special relativity is not about looks. It's about measurements made with clocks and rulers, about the core definitions of distance and time. Two observers can both be correct, while measuring different lengths and different times, because their motion changes how they slice reality into space and time. No human eye is required. No human perception is needed. Even if the universe were empty of life, these relationships would still hold. Because the effects are not psychological, they are geometric. This is the part that makes everything feel more ancient, not less. Because special relativity reveals that space and time were never truly separate. We only treated them that way because at human speeds, the difference is invisible. In reality, space and time are braided together into a single fabric. Space-time, not as a metaphor, as a structure. And motion is not merely moving through space. It is a rotation through space-time, a rebalancing between how much of your journey is through space and how much is through time. The faster you move through space, the less you move through time compared to someone else. This is why time dilation is not a strange add-on. It is the natural consequence of living in space-time. Now we can see what the speed of light really is. It is not just how fast light goes. It is a boundary built into the geometry of space-time, a conversion rate between time and space, a deep constant that tells the universe how events can be connected. This is why light is special, not because it's bright, not because it's beautiful, but because it traces the edges of what causality can do. At the speed of light, the separation between space-like and time-like paths becomes absolute. Light doesn't merely move fast, it moves on the boundary of space-time itself, and that boundary is the reason cause and effect remain coherent. It is the reason the universe doesn't dissolve into paradox. Special relativity did not destroy classical physics the way a hammer destroys glass. It destroyed it the way a tide erases a line drawn in sand. Slowly, completely. Because at everyday speeds, classical physics still works. It still builds bridges and airplanes and cities, but under the surface, the old picture is gone. There is no universal time. There is no rigid space. There is no shared now stretching across the cosmos. There is only space-time, and within it, a speed that cannot be exceeded because it is not a limit imposed from outside. It is a limit written into the universe's shape. But this creates a bigger problem. If light speed is not just a speed, but a structural boundary, then what happens when we try to push matter toward it? What happens to something with mass, something heavy, stubborn, resistant, when we demand that it chase a boundary that space-time itself protects? Because light can live on that edge. It is massless. It doesn't pay the same price. But objects with mass have to pay. And the closer we drive them to that limit, the more the universe demands in return. Not in philosophy, in energy, in an impossible cost that grows without mercy. And once we understand that cost, we begin to see why the limit is not negotiable, not for rockets, not for civilizations, not for any technology we can dream into existence, because the barrier is not built by engineering, it is built by mass itself. There's a moment in every chase when we realize the thing we're chasing isn't running away, it's simply unreachable. Not because we're weak, not because our engines are primitive, not because we lack imagination, because the universe has built something into reality that feels like a wall. Without ever placing a wall in front of us, we can keep accelerating, we can keep spending fuel, time, and ambition. And yet, the closer we get to light speed, the more the universe responds like a tightening fist, not with violence, with mathematics so calm it feels cruel. And that's when the true cost of acceleration appears. In our everyday world, speed feels like a simple deal. Press the pedal harder. The car responds. Push longer. You go faster. Even in the sky, the pattern feels familiar. A jet climbs, burns fuel, and reaches cruising speed. A rocket stages, dumps mass, and gains more speed. So we learn a story that feels universal. More energy means more speed. But the cosmos has a threshold where that story stops working, where speed becomes less like a ladder and more like a trap. Because the closer we drive matter toward light speed, the less speed we buy with the energy we spend. And eventually it becomes almost nothing. We keep paying, but we stop gaining. Picture this. We're pushing a heavy shopping cart down a long hallway. At first, it's honest. We push, it rolls. We push harder, it rolls faster. But then imagine the hallway is strange. The faster the cart goes, the heavier it becomes. Not in our hands, inside the cart itself. As if the universe is quietly adding weight as a penalty for speed. So each time we try to increase its pace, we feel more resistance than we did before. We're still pushing, but the cart is no longer the same object. That's the closest everyday picture we can give to what happens in relativity. The faster an object with mass moves, the more stubborn it becomes against further acceleration. It's as if motion itself increases inertia, and eventually, the universe demands a price so steep that no finite push can pay it. To understand this, we have to stop treating speed like the only thing that matters. In classical thinking, motion is mostly about velocity. But in relativity, motion is also about how energy and momentum behave near the cosmic limit. Here's the core truth. Massive objects cannot reach light speed because doing so would require an unlimited amount of energy. Not a lot, not a ridiculous amount. Unlimited, no final number, no finish line, just an endless climb. And this isn't a technological limitation. It's not about better rockets. It's not about smarter engineering. It's about what mass is. Mass is the universe's way of making objects resist being pushed into the domain where only light belongs. When physicists say it would take infinite energy, it can sound like a dramatic phrase. So we need to make it plain. Infinite doesn't mean more than all the fuel on Earth. It doesn't mean more than the sun could provide. It means there is no amount that completes the task. No matter how much energy we add, we can always get closer. But we never arrive. It's like trying to reach the horizon by walking toward it. You can walk all day, and the horizon stays ahead. But this is worse because in this case your legs get heavier with every step. The universe isn't teasing us. It's enforcing a boundary. At low speeds, energy behaves the way we expect. Double the push, get more speed. But as we approach light speed, the relationship becomes warped. Each additional increase in speed costs more energy than the increase before it. Not by a little, by a compounding, unforgiving factor that grows rapidly. So going from slow to fast is expensive. Going from fast to near light speed is monstrous. And going from near light speed to light speed is not expensive at all. It's impossible. Because the price does not converge, it diverges. The closer we get, the more the universe demands, and the demand never stops growing. This isn't just theory whispered into textbooks. We have built machines that slam into this limit every day. At CERN, at the Large Hadron Collider, the LHC, they accelerate protons to speed so close to light speed that the difference becomes almost absurd to say out loud. The important part isn't the exact decimal. The important part is what they discover. Once those particles are already extremely close to light speed, adding more energy doesn't make them noticeably faster. Instead, the added energy shows up as greater momentum, greater collision power. The universe lets them become more violent, but it refuses to let them cross the boundary. That's the signature of a fundamental limit, a limit that holds even when we bring some of the most precise instruments humans have ever built. Not because the machines are weak, because space-time itself is strict. Let's translate what near light speed feels like. Light speed is about 300,000 kilometers per second, about 186,000 miles per second. At that speed, you could cross the United States, about 2,450 miles, around 3,940 kilometers, in about 1/100th of a second. You could circle Earth multiple times in a single second. And yet, if we built a spacecraft that could travel at even 1/10th of light speed, about 30,000 kilometers per second, around 18,600 miles per second, we would still need more than 40 years to reach the nearest star system. That's longer than a childhood, longer than most careers, longer than the time between generations. And that's only 1/10th of the limit. So when we talk about catching up to light speed, we're not talking about pushing a little harder. We're talking about entering a regime where the universe begins charging us like it's protecting something sacred. Here's a helpful way to think about it. In relativity, energy is not just fuel. Energy is a kind of currency space-time accepts and then redistributes according to its laws. When we add energy to a slow object, space-time mostly pays it out as speed. But when we add energy to an object already near light speed, space-time stops paying out in speed. It pays out in resistance, in momentum, in the intensity of what happens when it collides. It's like trying to speed up a clock by turning the dial past its limit, only to discover the dial turns smoothly, while the clock refuses to tick faster. The energy isn't wasted, it just doesn't buy what we wanted. Light can travel at light speed because light has no mass. It doesn't have to be pushed up to that boundary. It lives on it naturally. But anything with mass is different. Massive objects carry a deep constraint. They always move through time in a way light does not. They have proper time, a private ticking that never disappears as long as mass remains. And that is why they cannot join light on the boundary. Because to do so would require a complete trade. All motion through time would have to be surrendered, and mass refuses that surrender, not emotionally, physically. It's as if mass is the universe's signature that says, this thing belongs to the realm where time must continue, and light belongs to the realm where time does not behave that way at all. This is where our futuristic fantasies often quietly die. We imagine better engines, more powerful fuel, advanced propulsion. We imagine a civilization that simply scales up what we do now. But the limit isn't sitting in our technology, it's sitting in the structure of how energy and motion relate. Even with perfect engineering, no waste, no heat loss, no inefficiency, the energy cost still climbs without mercy. Because the barrier is not mechanical, it's geometric, it's built into space-time. So the dream of just keep accelerating until we hit light speed is like trying to dig through the concept of north. No matter how strong the shovel is, it's not the kind of thing you can break. What makes this truly disturbing is that mass isn't just stuff. Mass is a rule. It's the reason objects have inertia. It's the reason acceleration requires effort. It's the reason energy has to be paid at all. And near light speed, mass reveals itself as an enforcer. It's as if mass stands at the edge of the limit and says, You can approach, you can spend, you can sacrifice, but you will not cross. This is why light speed is not merely a speed limit, it's a boundary between two kinds of existence, things that must live inside time and things that do not. And now, place yourself inside it. Imagine you're in a spacecraft that can accelerate smoothly, endlessly. No vibration, no sound, only a steady pressure against your seat. At first, the stars ahead look normal, but as your speed climbs, something inside the universe begins to tighten. You can push harder, you can burn more fuel, and you can watch the speedometer climb, but the gain starts to feel smaller and smaller and smaller until it becomes almost cruel. You are spending enormous effort for a whisper of progress. The ship is not failing, reality is resisting you, and you begin to understand what this limit really is. Not a barrier in space, a barrier in the relationship between mass and motion. So the deepest correction we have to make is this: we cannot think of light speed as something we might eventually reach. For anything with mass, light speed is not a destination, it is an asymptote, a boundary we can approach forever without touching. And that's why no object can ever catch up. Not because we are small, but because the universe is consistent. Preserves its structure by demanding that massive objects remain on one side of the boundary. And that consistency is what keeps causality stable. It's what keeps the universe from turning into a chaos of contradictions. The speed limit is enforced not by an external force, but by the internal bookkeeping of space-time itself. But then, the story turns sharper, because if we can't reach light speed, what exactly is being protected? Why does mass enforce this boundary with such ruthless precision? What is the universe trying to prevent? Because the closer we get to the limit, the stranger the trade becomes. Speed stops being the main drama, and something else steps forward. Quietly, inevitably, the behavior of time itself. Not as a background, not as a passive river, but as the deeper currency we are truly spending every time we try to go faster. We've been calling it a speed limit, because that's how it looks from where we stand, in bodies that move slowly, under skies that feel still. But the closer we stare at this boundary, the more unsettling it becomes, because light speed isn't just about how fast something can travel through space. It's about something deeper, something quieter, a limit on how reality can unfold, a limit on how time itself can flow. And once we understand that, the cosmic speed limit stops feeling like a wall in the distance. It starts feeling like a rule written into the meaning of before and after. Every living thing carries a private clock, not the clock on the wall, not the clock on our phone, a deeper one, the steady rhythm of change, a heartbeat, a thought forming, a chemical reaction inside a cell, a candle flame consuming wax. That inner rhythm, our own experience of duration, is not merely a feeling. In relativity, it has a name. It's called proper time. Proper time is the time measured by a clock that travels with you. The time measured along your own path through space-time. It's what your body experiences as now becoming later. And here's the strange part. Proper time is not guaranteed to match someone else's. Not if we're moving differently. Not if we're living different paths through space-time. That is not philosophy. It's physics. Imagine this. Two identical clocks sit side by side on a kitchen table. We press start. They tick together. Quiet, ordinary, honest. Then we take one clock and place it on a plane. The plane takes off, circles the planet and comes back. We set the travelling clock down beside the one that stayed home. Both clocks still work, both clocks still tick, but they no longer agree. The travelling clock shows less time has passed, not because it was damaged, because the path it took through space-time was different. This has been measured with atomic clocks, real, precise clocks, carried on, aircraft, and compared to clocks on the ground. Time didn't seem different. Time was different. And once we accept that, we're forced to confront the deeper truth hiding behind light speed. The universe doesn't just limit motion through space, it limits the relationship between motion and time. Light speed is not only the speed of light, it is the conversion between space and time inside the fabric of space-time. It tells us how tightly the universe binds distance to duration. It is the rate at which causality can stitch events together, because every cause must reach its effect, every influence must travel, every signal, every physical link between events has to move through the universe somehow. And the universe has decided that this stitching process has a maximum pace. That maximum pace is light speed, not because light is special as a substance, because light speed is how space-time protects order. It's how the universe makes sure that before remains before, and after remains after. But then it gets stranger, because if light speed is the maximum speed through space, it quietly becomes the minimum speed through time. That sounds impossible. Until we remember what relativity revealed, we are always moving through space-time, even when we feel still. When we're sitting still relative to Earth, most of our motion is through time. Our seconds pass normally. Our bodies age normally. Our thoughts move forward in a steady stream. But as we move faster through space, the universe forces a trade. More motion through space, less motion through time. That is time dilation. And the closer we approach light speed, the more extreme the trade becomes. Time slows, not for the outside world, for us, for the clock traveling with us, for the processes happening inside our skin, for the private river of proper time. The universe begins to ration time. Proper time is unsettling because it feels intimate. It's not a distant concept about stars. It's about our own continuity, our own becoming. Proper time is what a wristwatch measures when it never leaves our arm. It's what a heart measures by beating, and relativity says, different journeys produce different amounts of proper time. The universe does not guarantee equal aging. Equal duration is not a universal gift. It's a local experience, a consequence of our path. And speed changes that path. We don't need science fiction to see this. Nature provides its own laboratory. High above us, cosmic rays strike Earth's atmosphere and create particles called muons, short-lived particles that decay quickly. At rest, muons should vanish before they can travel very far. And yet they reach the ground. They appear in detectors. They arrive inside our world. Why? Because they're created moving so fast that their proper time runs slower relative to Earth. From our perspective, their internal decay clock is stretched. From their perspective, the atmosphere is compressed. Two descriptions, one reality. The universe keeps both true by letting time and distance reshape themselves, so that light speed remains the same. This is not a story we invented. It's a story the universe demonstrates above our heads, every day. Now we can see what Chapter 4's infinite energy really hides. It isn't just that engines can't push us past light speed. It's that approaching light speed demands something the universe won't give up. It demands our time. Because as we push closer and closer to that boundary, our proper time slows more and more. Our seconds become stretched compared to the outside world. The universe begins to treat time like a scarce resource, like oxygen in a sealed room. We can still breathe, but less and less arrives per moment, until we can't ignore the conclusion. Here's where the story turns severe. Light itself does not experience proper time the way we do. Light follows paths where, in the language of relativity, the passage of proper time is different. That's why light can live on the boundary. It doesn't need to spend time the way massive objects do. But anything with mass carries proper time like a signature. As long as mass exists, there is a private ticking, a private unfolding, and to reach light speed would mean pushing that ticking to zero. It would mean surrendering time entirely. For a massive object, that surrender cannot be completed, because mass belongs to the realm where time must continue. So as we accelerate closer to light speed, our proper time slows toward a kind of limit. We can get extremely close, but we never reach time stops, because we never reach light speed. The wall is not only about speed, it's about what it would do to time. Now place yourself inside it. Imagine you're in a spacecraft that can accelerate smoothly, silently, no shaking, no roaring, just a steady pressure like a firm hand against your back. Outside the window, stars distort into sharper points. The darkness feels deeper. You check a clock on the dashboard. It ticks normally. Your breathing feels normal. Your thoughts arrive in their usual rhythm. Nothing inside you announces that anything has changed. But far behind you, on Earth, our clocks are beginning to pull ahead. Not dramatically at first, but steadily, relentlessly. And if you keep accelerating, closer and closer to that cosmic limit, you return to a universe that has aged more than you have. Not because you cheated time, because time itself was rationed along your path. And that realization doesn't feel like power. It feels like a rule. So the ultimate reframing is this. Light speed is the boundary between different kinds of time experience. It is the boundary where the relationship between space and time reaches its extreme. It is the edge of how the universe permits clocks to behave. And that is why it is universal. Not because the universe chose a speed like an arbitrary law, but because space-time has a structure, and light speed is the structural constant that keeps that structure coherent. It ensures there is a maximum pace at which cause can reach effect, a maximum pace at which any influence can propagate, and it ensures that the geometry of space-time doesn't allow contradictions to leak in. This is why the limit matters. Not because it frustrates our dreams of faster travel, but because it protects meaning. Because causality, the order of events, is not just a human preference. It is what allows the universe to be a story at all. If causes could outrun the limit, effects could appear before their causes. We wouldn't just break physics, we would break sequence. We would break the difference between memory and prediction. We would break the entire idea that the universe moves forward from one state to the next. Light speed is the pace at which reality allows itself to be updated, event by event, signal by signal, influence by influence. It is the speed at which the universe keeps its bookkeeping honest. But then we arrive at the most disturbing implication. If light speed is really a time limit, then anything that tries to exceed it isn't just moving too fast. It's trying to rearrange time itself. It's trying to reach effects without paying the full cost of causation. And that raises a question the universe does not let us ignore. What would actually happen to cause and effect if information could travel faster than light? Because the moment we imagine breaking this limit, we don't just imagine a faster spaceship. We imagine the order of reality becoming negotiable. And once the order becomes negotiable, paradox isn't a thought experiment anymore. It becomes a physical threat. There's a quiet assumption beneath everything we do. We drop a glass, and it shatters. We strike a match, and a flame appears. We speak a word, and only then does it reach someone else. Cause first, effect second. So natural we barely notice it. But the universe doesn't owe us that order. It enforces it, and the enforcement is not emotional, not philosophical, not cultural. It's physical. It is written into space-time as a single, severe rule. No information gets to outrun light. Not because light is sacred, because if anything could outrun it, the order of reality would become negotiable. And that is where everything breaks. We've been treating light speed like a ceiling on motion, but its deeper job is stranger. It keeps the universe from disagreeing with itself. Because cause and effect is not just a story we tell. It's the mechanism that allows events to form a coherent chain at all. If we send a signal, the signal has to travel. If we push an object, the influence has to propagate through atoms. If the sun changes, its effects don't appear instantly everywhere. Gravity changes propagate too. Even NASA and ESA navigate spacecraft by respecting this delay, this finite pace of influence, because the universe won't deliver information faster than it allows. Light speed is the maximum speed of cause. It is the pace limit on reality's ability to update itself. And once we understand that, we start to see why trying to go faster than light isn't just ambitious, it's catastrophic. Imagine this. We're standing in two distant buildings at night, separated by a wide river and dark streets. We each have a flashlight. We agree on a simple plan. When one of us turns on the light, the other sees it and turns theirs on in response. A clean chain, a cause, an effect. Now imagine we are not standing still. Imagine one building is moving, like a train sliding through the night, fast enough that motion itself matters. In our daily lives, that doesn't happen. But the universe does not care what is daily. At high speeds, the order of events becomes something space-time computes differently for different observers. And that creates a terrifying possibility. If a signal could travel faster than light, some observers would see the reply happen before the original message was sent, not as a trick, not as confusion, as a real reversal in the time order of events. And once time order can reverse, cause and effect no longer have a stable meaning. This is the part we have to face directly. There is no single cosmic clock that all observers share. There is no universal now spread across the universe like a flat sheet. Albert Einstein's relativity doesn't just say time can stretch, it says something more disturbing. Simultaneity itself is relative. Two events that are at the same time for us are not necessarily at the same time for someone moving relative to us. That isn't a side detail. It's the core reason faster than light information is forbidden. Because if there's no universal now, then any attempt to send information faster than light becomes an attempt to jump across a shifting landscape of time definitions. And when you jump across that landscape, you can land in someone else's past. In classical thinking, faster than light just means faster delivery. Same direction, same order, just quicker. But relativity changes the meaning of quicker because different observers slice space-time differently into space and time. Here's the strange part. If a signal travels faster than light in one observer's frame, there will always exist another observer, moving relative to the first, who measures that signal as traveling backward in time. This isn't speculation. It's a direct consequence of how space-time handles time order when simultaneity is not absolute. And once a message can be received before it is sent, the universe loses its ability to maintain a consistent causal chain, because then we can build loops, and loops are where reality fractures. Picture a long hallway with two doors at opposite ends. We stand in the center with a stopwatch. Two friends stand at the doors, each holding a bell. We shout "now," and both ring their bells at the same time. We hear them together. To us, simultaneous. But now, imagine we're walking quickly toward the left door when they ring. We're moving toward the left sound, away from the right sound. The left bell reaches us sooner. The right bell reaches us later. And because sound has a fixed speed through air, we would conclude the left bell rang first. Same hallway, same bells, same physical events, different time order, created by motion and finite signal speed. Now replace sound with light and make the speeds extreme. That's relativity's world. And now imagine a signal that ignores this rule, one that travels faster than light. It wouldn't just arrive sooner. It would slice through the fragile agreement that keeps time order stable between observers. If faster than light signals existed and could carry usable information, then we could do something that should feel immediately wrong. We could arrange for an effect to prevent its own cause. Not metaphorically, mechanically. Because once one observer can send a message into another observer's past, we can build a two-step exchange. One message goes faster than light one way. A reply goes faster than light back. And due to the relativity of simultaneity, The combined exchange can form a loop where the reply arrives before the original message was sent. This is not a fantasy about time machines. It's a simple consequence of mixing faster than light information, with observers moving relative to each other, in a universe where now is not universal, and the moment we can create a loop, causality becomes unstable, because then the universe must answer a question it cannot answer consistently. What happens when an event both happens and doesn't happen, depending on whether it prevents itself? That's when physics stops being a description of reality and becomes a contradiction. So light speed isn't just a maximum speed, it is the boundary that separates two kinds of connections between events. Time-like connections, where cause can influence effect without paradox. Space-like separations, where no causal influence is allowed because different observers disagree on time order. Light speed is the fence line between these regimes. Inside the fence, cause and effect remain consistent. Outside the fence, before and after are no longer agreed upon, and the universe does something firm and elegant. It forbids information from crossing that boundary, not as a moral decision, as a structural necessity, because if we allow information to move faster than light, we allow information to move into regions where time ordering is not stable, across observers. And if time ordering is not stable, causality becomes optional. The universe cannot survive optional causality, not as a coherent system. Now, let's put you inside the danger. Imagine you're in a spacecraft moving at a significant fraction of light speed, gliding through darkness so deep it feels like a pressure. You receive a signal, some message from Earth. If that message is limited by light speed, it can only arrive after it is sent, no matter what. It can be delayed, it can be distorted, but it cannot arrive before its own origin. That's the quiet safety of the limit. But if we imagine, even for a moment, a signal that outruns light, then depending on who is moving and how fast, there are frames of reference where you receive the message before Earth ever decided to send it. And the moment you can act on that message, you can change the decision that created it. You can poison the chain at its root. That is what faster than light information threatens. Not faster travel, not better communication, the integrity of time itself. It's tempting to treat this as philosophy, a word game, a what if. But physicists don't fear paradoxes because they are emotionally uncomfortable. They fear them because they destroy predictive law. If the universe allows causal loops, then the universe stops being computable, even in principle, not by humans, by reality, because laws depend on well-posed questions. Given a cause, what effect follows? But if effects can reach backward and erase causes, then the question becomes ill-defined. And the universe, quietly, relentlessly, refuses to become ill-defined. So the speed of light becomes a kind of protection, a safeguard, a structural immunity against contradiction. This is the deepest conclusion we can draw without romance. If special relativity is true, and if different observers can disagree about time order, then any mechanism that transmits usable information faster than light would enable causality violations. And since we observe a universe that remains stable, one where cause and effect hold with extraordinary consistency, physics concludes that faster than light information transfer does not occur. Not in any controllable way, not in any usable way. Nature can be mysterious, it can be strange, but it is not self-contradictory. That's why, even in the most advanced theories and experiments, the speed of light remains untouched as the maximum speed of information and causal influence. It is the rule that keeps the universe from unraveling. But then a deeper question rises, one that doesn't let us rest. We've been talking as if space-time is a calm, flat arena, as if the geometry is simple and only our motion complicates it. Except the universe is not flat. It is curved by mass and energy. Gravity doesn't just pull on objects, it changes the stage beneath them. And that creates a new pressure point in the story. If space-time itself can bend, twist, and curve, does the speed limit survive inside that curvature? Does gravity create loopholes? Or does the universe enforce the same boundary even more deeply, not as a rule for light, but as a rule for space-time itself? We've been speaking as if space-time is a calm, level floor, a clean grid where events happen, and light draws straight lines across it. But that picture was always a comfort, because the real universe is heavier than that. Massive, crowded with stars, galaxies, black holes. And mass doesn't just sit inside space-time like furniture in a room. Mass reshapes the room. It bends the floor beneath the story. And that raises a question that doesn't feel philosophical at all. It feels surgical. If space-time itself can curve, does the speed limit survive inside that curvature? Or does gravity create loopholes, hidden pathways where light speed stops being the law? Because if gravity can alter geometry, then maybe geometry can alter the limit, and that thought is dangerous. For centuries, gravity felt like a kind of invisible command, a force that reached across emptiness, a pull that seemed immediate. In Isaac Newton's world, gravity didn't need a messenger. It simply was. The sun pulls Earth, Earth pulls the moon, everything influences everything else across the void. It worked brilliantly. It predicted orbits with astonishing precision, but it left an uncomfortable wound in the logic. How does a force act across nothing? How does the universe know instantly what to do across millions of kilometers, across millions of miles? Because if gravity were truly instantaneous, it wouldn't just be powerful, it would be faster than light information. It would violate the very boundary we just discovered protects cause and effect. So either gravity was an exception, or our understanding of gravity was incomplete. And that's when Albert Einstein went deeper than special relativity. He didn't just ask how objects move, he asked what space and time are. Imagine this. We're in a dark room with a trampoline stretched tight, flat, calm, perfectly even. Now we place a heavy bowling ball in the center. The trampoline dips, not because it's being pulled, because the surface itself has changed shape. Now we roll a marble across that surface. The marble curves inward. It looks like a force is grabbing it, but what's really happening is simpler and more disturbing. The marble is following the straightest possible path on a curved surface. This is the core insight of general relativity. Gravity is not a force reaching through space. Gravity is space-time geometry changing the definition of straight. Matter tells space-time how to curve. Curved space-time tells matter and light how to move. And once we see gravity this way, the speed limit stops feeling like a rule imposed on objects. It becomes a rule woven into geometry itself. Here's the strange part. In general relativity, light still does what it always does. It always moves at light speed locally, even in gravitational fields, even near massive objects, even near black holes. Gravity can bend light's path. It can delay it. It can redshift it, stretching its wavelength. But it does not allow light to break the fundamental boundary. It cannot create a region where information outruns light in the local sense, because gravity isn't a different system. It's the shape of the same space-time that special relativity described. So the speed limit isn't a law sitting on top of physics like a commandment. It's a feature of the stage itself. No matter where we go, we carry that geometry with us. This is where the story becomes visually haunting. Light doesn't always travel in the straight lines our eyes expect. When starlight passes near the sun, it is deflected. That isn't theory. It was measured during a solar eclipse in the early 1900s, when astronomers compared star positions near the eclipsed sun to their normal positions. The stars appeared slightly shifted, not because the stars moved, because space-time near the sun is curved, and the light had to follow that curvature. So light can be bent, but it cannot be outrun. That distinction matters, Because bending is not cheating, bending is geometry. The limit is still enforced, quietly, universally, because the rules of causality travel with the structure of space-time. Now, we reach the place where the story tightens. If gravity is geometry, then changes in gravity are changes in geometry. And geometry doesn't change magically. It has to propagate, it has to travel, it has to move through the universe as information. So the question becomes unavoidable. When something massive shifts, when black holes merge, when neutron stars collide, how fast does the change in gravity spread outward? If gravity respected the same limit as everything else, it should travel at light speed. But if gravity were an exception, then the universe would have a faster-than-light messenger built into its own structure, and that would open the door we've been terrified to open, a loophole in causality, a crack in the order of reality. This is why scientists didn't treat this as a small technical detail. They treated it as existential, because the speed of gravity is the speed at which the universe updates its own geometry. For a long time, gravitational waves were a prediction, beautiful, severe, untested. Einstein's equations implied them, but the universe doesn't care what our equations imply. It only cares what it does. Then, in 2015, the LIGO detectors, LIGO, heard something, not with microphones, with laser interferometers so sensitive they could register changes smaller than the width of an atom. A signal swept through Earth, a rising, tightening chirp. Two black holes had merged, and space-time itself had shivered. It was the first direct detection of gravitational waves, and it changed everything, but it still left one open wound. We could detect the waves, yet we still needed to confirm how fast they traveled. Because detecting a ripple is not the same as measuring its speed. The universe had one more test to pass. In 2017, a different kind of collision shook the cosmos. Two neutron stars spiraled together and merged, and this time the universe didn't only send gravity, it sent light. Gravitational waves arrived. And then, almost immediately after, telescopes detected a burst of gamma rays, followed by light across the spectrum as observatories around the world watched the aftermath. The key point wasn't just that we saw it, it was that the gravity signal and the light arrived separated by only a tiny amount of time after travelling an unimaginably long distance, about 130 million light-years. That means the signal began its journey when dinosaurs still ruled Earth's skies and forests, long before humans existed, long before our species even had a chance to appear. And after crossing that abyss, gravity and light arrived almost together. Not perfectly identical in timing, because the astrophysics of the explosion can produce slight delays between the moment the merger happens and the moment light escapes, but close enough to show something profound. Gravity does not outrun light as a usable messenger. It travels at the same cosmic limit, within extremely tight bounds. The universe sealed the loophole. No secret faster channel. No hidden exception. Because if gravity could propagate faster than light, we wouldn't just gain a new speed. We would lose the integrity of cause and effect. We would have two separate update systems for reality, one for light and matter, and one for gravity. And those two systems could disagree about time ordering. They could create contradictions, situations where geometry updates before the events that cause the update. The universe would become unstable in the deepest sense. So when gravitational waves are observed behaving like light in this crucial way, we're seeing something beyond an astrophysical detail. We're seeing the universe protect its own coherence, the same way a living organism seals a wound. Now the story becomes almost cold in its clarity. General relativity doesn't allow space-time to have special regions where causality is optional. Yes, space-time can curve violently. Near a black hole, paths twist in ways our intuition can barely hold. Time dilates. Light can orbit. Signals can be delayed, but the limit still functions locally. The rule still holds at the point where physics actually happens. Even when the geometry becomes extreme, information doesn't gain a faster lane through the fabric. Instead, the geometry itself determines what paths are possible and which paths are forbidden. It's like a mountain landscape. There is no straight line across it in the naive sense, but every traveller is still bound by the same local constraints of motion. The terrain can lengthen the journey. It can bend it, it can trap it, but it doesn't permit a traveller to break the deepest law of the land. And if you could stand near an immense gravitational field, near a neutron star for example, your body wouldn't feel a cosmic rule being enforced. You'd feel weight, pressure, a kind of crushing insistence from the environment. But the deeper enforcement would be invisible. Your radio signals would still not leap beyond the limit. Your light would still not outrun causality. Even your sense of now would become more local, more private, more isolated from distant regions. And you would realize something unsettling. Gravity can make the universe feel more extreme, but it does not make the universe less consistent. It bends the stage without breaking the script. This is one of the hardest truths to accept, because we love the idea of hidden corridors, secret shortcuts through the cosmos. Some region where physics relaxes, some crack in the structure. But general relativity is ruthless. It says space-time can be flexible, yes, but it is not permissive. It is not a playground. It is a disciplined geometry where cause and effect are preserved by the same boundary everywhere. The universe does not protect the speed of light because it loves light. It protects it because it is protecting causality. And causality is what allows the universe to be an ordered reality instead of an incoherent blur. But then we run into a statement that sounds like a contradiction, a statement that has confused even intelligent people for decades. We've said nothing can travel faster than light. We've said no information can outrun the limit. And yet, when astronomers look out into the deep universe, they describe something that seems to violate it. Galaxies so far away that they are receding from us faster than light. Not because they're rockets, not because they're breaking the rules, because space itself is expanding. And that raises the next question. Sharp, immediate, unavoidable. If space-time is the stage, and the stage itself can stretch, then what does faster than light even mean when it's the space between things that is growing? Somewhere in almost every conversation about relativity, someone says a sentence that feels illegal. Galaxies are moving away from us faster than light. It lands like a crack in the room, because we've just spent so long building something sacred, the cosmic limit, the boundary that protects cause and effect, the speed that space-time refuses to let us cross. So when we hear faster than light in a real scientific context, it sounds like the universe is contradicting itself. But then the deeper truth arrives. The galaxies are not breaking the rule. The rule is being misunderstood. Because the universe has two different kinds of motion, and only one of them is constrained by light speed in the way we usually imagine. There is motion through space, a rocket accelerating, a planet orbiting, a star drifting through a galaxy. That kind of motion is local, physical, measurable with clocks and rulers right where the object is. And for that kind of motion, the limit is ruthless. Nothing with mass reaches light speed. No signal outruns light. No cause escapes its own future. But then there is something else. Motion of space itself. Not objects flying through a fixed stage, but the stage stretching between objects. And this second kind of motion does not behave like a rocket. It is not a thing traveling inside space. It is the metric of space-time changing, distance itself evolving with time. And that difference is everything. Picture this. We draw two tiny dots on a rubber band with a marker. Those dots are not sliding along the rubber. They're not moving in the usual sense. Now we stretch the rubber band. The dots separate. From the perspective of one dot, the other dot is receding, and the farther apart the dots are, the faster their separation grows when the band stretches. At a small scale, the separation is modest. At a large scale, it becomes dramatic. Here's the key. Neither dot is breaking any speed limit on the rubber band itself. They're just being carried apart by the stretching of the band. That is cosmic expansion. Galaxies aren't always racing through space like bullets. Many are, in a sense, sitting in place in the expanding fabric, and the fabric itself is growing between us. So how can a galaxy be faster than light away from us? Because the phrase faster than light is hiding a trick. It's comparing two different things: the speed limit for local motion through space-time, and the rate at which large-scale distances between distant regions of space-time increase. A galaxy can be carried away by expanding space so quickly that its distance from us grows at more than light speed. But that doesn't mean the galaxy is locally moving through space faster than light. It means the gap is inflating, and that distinction is why relativity remains intact. The discovery that the universe expands is one of the quiet earthquakes in science. In the early 20th century, astronomers like Edwin Hubble observed that distant galaxies are, on average, redshifted, their light stretched toward red. That redshift isn't just a Doppler effect from galaxies flying away like cars on a highway. On the largest scales, it's largely the stretching of light itself as space expands during the light's journey. Light leaves a galaxy with a certain wavelength. While it travels, the universe grows. So by the time it reaches us, its wavelength has been stretched with the fabric. The message arrives older and longer and redder. And this expansion is not a rumor. It's supported by multiple lines of evidence: galaxy redshift surveys and the cosmic microwave background, the afterglow of the early universe measured by missions like NASA's WMAP and ESA's Planck. So, the expansion is real, but it introduces a dangerous misunderstanding. If space expands, then distance can grow without anything locally exceeding light speed. And if distance can grow that way, then recession speeds can exceed light speed without breaking causality. We use the word speed as if it always means the same thing. But in cosmology, recession speed is not the same as velocity through space. It's a rate of separation due to expansion, and because expansion acts on distance, the farther away something is, the larger that rate can become. There is a rough scale where this becomes dramatic, often called the Hubble radius in everyday explanations. Beyond a certain distance, the expansion of space can make the separation grow at more than light speed. Again, not a rocket, not a chase, a stretching of the ruler itself. This is why extremely distant galaxies can be receding from us faster than light and still send us light that we can observe, because the light was emitted when they were closer, and the expansion history of the universe matters. It's not one simple snapshot, it's a long, evolving geometry. Now we reach the part where people instinctively try to exploit the loophole. If space can move faster than light, why can't we use it? Why can't we ride expansion the way a surfer rides a wave? Because cosmic expansion is not like a wind you can harness. It's not a flow you can steer into. On scales where gravity holds structures together, solar systems, galaxies, clusters, the expansion is effectively overwhelmed by local binding. Your atoms do not expand. Your body does not stretch. The Milky Way does not inflate like a balloon. Expansion is a large-scale behavior of space-time when averaged over vast distances. It's like the tide in an ocean. You can float in it, yes, but you can't build a boat that uses the tide to instantly jump from one continent to another. The tide changes the separation of shorelines over time. It doesn't give you a local engine that breaks the rules of motion. And even more importantly, to send a message, you need a causal chain, an influence traveling through space-time. Cosmic expansion does not create a path where a signal locally outruns light. It changes how far the signal must travel and whether that travel is even possible over cosmic times. In many cases, expansion makes communication harder, not easier. Now place yourself inside the strangest consequence. Imagine you are in deep intergalactic space, far from stars, far from the familiar glow of home. You look out at the universe and see countless galaxies, but many of them are already beyond a boundary you cannot cross, not because your ship is weak, but because of expansion. Even if you send a beam of light toward them, the space between you and them can expand so relentlessly that the beam will never arrive. Not because the beam slows down, because the destination runs away in a geometric sense. This is what a cosmic horizon feels like. Not a wall of matter, a limit of connection. A region of the universe that is not forbidden by force, but separated by the evolving geometry of space-time. And suddenly the universe feels less like a place, and more like a story with chapters you cannot turn to. Here's where the story becomes precise. In relativity, especially in general relativity, some speeds depend on coordinates. The universe doesn't come with a built-in global ruler that everyone must use. We choose coordinate systems to describe expansion, distance, and time slicing. In those coordinates, we can define a recession speed that can exceed light speed, but that is not a local physical speed measured by an observer next to the object with a radar gun. Locally, in any small patch of space-time, special relativity still holds. Locally, no observer measures light being overtaken by a material object. Locally, causality remains protected. This is why cosmologists can calmly say, recession faster than light, without claiming the universe is broken. They are describing how distance between co-moving points changes in an expanding metric, not how objects blast through space. The distinction sounds technical, but it is the difference between contradiction and coherence. Imagine bread dough with raisins inside. The raisins aren't crawling through the dough, but as the dough rises, every raisin moves away from every other raisin, and the farther apart two raisins are, the faster their separation increases as the dough expands. No raisin breaks a local speed limit in the dough. They're simply being carried apart. That's cosmic expansion. And it also explains something haunting. Every galaxy sees other galaxies receding. There is no central point where everything expands from like an explosion into pre-existing space. Space itself is expanding everywhere, which means the motion is not from a single source. It's in the fabric. If some galaxies are receding faster than light, why do we see them at all? Because what we observe is not a single moment. We're looking back in time. Light, we receive now, left its source long ago, sometimes billions of years ago. The universe was smaller then. The geometry was different. Some galaxies we see today were once within a region where their light could reach us. Over time, expansion carried them farther away. In some cases, we can still receive old light emitted long ago, but signals they emit today may never reach us. That isn't because their photons are weak. It's because the universe's expansion has changed the causal structure of who can talk to whom. This is why the observable universe has a horizon, not a boundary of matter, a boundary of communication. So the clean conclusion is this: light speed limits local motion and local information transfer. Cosmic expansion describes the changing scale of distance between faraway regions of space-time. Those are different categories. A galaxy receding faster than light does not mean it is locally traveling through space faster than light. It means the space between us is growing in a way that increases separation faster than light could cross. And that growth does not allow us to send faster than light messages, because no signal locally outruns light. In fact, expansion creates horizons that make some communication impossible, even at light speed. The universe can stretch itself into a shape where reachable and unreachable become physical categories, not by force, by geometry. This is what makes the cosmos feel both elegant and cold. The universe doesn't need to break its own laws to create unreachable regions. It doesn't need to permit faster than light travel. It simply expands, and in that expansion, distance becomes something alive, something that evolves. We're not living in a static container. We're living inside a changing geometry, and the speed of light remains untouched, not as a limitation on imagination, but as the rule that keeps causality coherent in every local patch of reality, even while the stage grows beneath our feet. But then, inevitably, we face the next confusion. If cosmic expansion can make things seem to outrun light without breaking causality, what about the quantum world? Because quantum physics also produces effects that feel instantaneous, spooky, distant correlations that make people whisper the forbidden phrase again, faster than light. And now we have to be careful, because the quantum story is real, the correlations are real, but the misconception is also real, and the universe, once again, refuses to let information outrun its limit. There is one sentence that keeps returning, like a ghost we can't fully exorcise. Quantum entanglement is faster than light. It sounds like betrayal, because we've built a whole universe on the idea that light speed is the ultimate limit, the boundary that protects cause and effect, the rule that keeps before from collapsing into after. So when quantum physics enters the room, it feels like the universe is about to break its own spine. Two particles, separated by huge distances, and yet they behave like one system. Change one, and the other responds. Instantly. Or at least, that's how it feels from the outside. But then we slow down. We breathe. We look at what experiments actually show, and we discover something calmer and more unsettling. Quantum physics doesn't break the speed limit. It breaks our intuition, and those are not the same thing. Entanglement is not a signal traveling between particles. It is not a hidden beam. It is not a secret message whispering through space faster than light. Entanglement is a relationship, a single quantum state shared across distance, a kind of mathematical binding so deep that the best description of the system is not particle A and particle B. It's one system with two ends. This is why entanglement feels like magic, because we're used to the world being made of separate objects. Quantum mechanics says, sometimes separation is an illusion created by our scale, and when we measure one part of an entangled system, we don't send information to the other part. We reveal something about the shared state. That is the critical distinction. No message is traveling, a correlation is being exposed, and the universe treats correlations very differently than it treats signals. Picture this. We have two identical boxes. Inside each box is a light that can flash either red or blue. We close the lids. We separate the boxes. One stays with us, the other is carried far away, across oceans, across continents. Now we open our box. The light flashes red. Then far away, someone opens the other box, and they find blue. Not because blue arrived from our box, but because the pair was prepared with a shared rule. The results will be opposite. Now here's the part that matters. Before we open our box, we can't choose red or blue. We don't control the outcome. The flash is random, and because it's random, we can't use it to send a message. We can't encode language into it. We can't decide, if I want to say yes, I'll make red happen. Quantum mechanics doesn't give us that control. It gives us correlations that only become visible when results are compared later, using ordinary communication, limited by light speed. This is the heart of it. Entanglement creates powerful correlations, but it does not create controllable faster-than-light information transfer. Physicists didn't accept this calmly at first, because the implications were disturbing. In the 1930s, Albert Einstein, along with Boris Podolsky and Nathan Rosen, argued that quantum mechanics seemed incomplete because it allowed these strange long-distance correlations. Einstein famously disliked the idea, referring to it as spooky action at a distance, not because he was afraid of weirdness, Because he was defending causality, defending the speed limit. Quantum mechanics appeared to suggest that nature had either hidden variables, secret information we weren't seeing, or non-local correlations that defied classical expectations. For decades, this wasn't just philosophy, it was an experimental question, and eventually, experiments forced an answer. In the 1960s, the physicist John Bell found a way to test whether nature could be explained by local hidden variables. He derived inequalities, constraints that any local hidden variable theory must obey. Quantum mechanics predicted those constraints would be violated, so the universe was put in a box. Either the world is local in the classical sense, or quantum mechanics is telling the truth about something deeper. In the 1980s, experiments led by Alain Aspect and others tested Bell's ideas with entangled photons. Later experiments improved the setup, closing loopholes, making it harder and harder to explain the results with any local hidden variable story. And the outcome was brutal in its clarity. Bell inequalities are violated. The correlations predicted by quantum mechanics are real. In a deep sense, nature is not locally classical. That is the uncomfortable truth. But here's what did not happen. No usable, faster-than-light messaging was demonstrated. No causality collapse. No paradox machine. The speed limit remained intact, which raises the real question: how can the universe allow correlations that feel instantaneous, but still forbid faster-than-light communication? Here's the strange part. Entanglement gives us correlations, but each individual measurement result is fundamentally unpredictable. Even if we prepare the same experiment 1,000,000 times, we can't force a specific outcome for a single trial. We can predict statistics, we can predict patterns across many measurements, but the individual result arrives like a coin flip, except the coin flip is woven into the structure of reality. And this is why entanglement cannot be used to send information, because sending information requires control. It requires choosing between alternatives to encode a message. Binary, yes or no, 1 or 0. But quantum measurement outcomes don't obey our will that way. We can choose what we measure, what basis we use, what setting the detector has, but we cannot choose the outcome that appears. And that lack of control is not a technical limitation. It is built into the theory and confirmed by experiment. Randomness is the universe's lock. It lets correlations exist without letting messages travel faster than light. This is where everyday language fails us. We hear instantaneous correlation and we assume instantaneous communication. But communication means something precise. One side can deliberately influence what the other side receives in a way that transmits a chosen message. Entanglement does not do that. If we measure our particle and get a result, we immediately know what the other side would get if they measure in the same compatible way. But the other side doesn't know what we got, not until they receive a classical message from us by radio, fiber optic cable, light itself, limited by light speed. So entanglement feels like a shortcut, but it isn't. It's a relationship that only becomes visible when ordinary, slower-than-light communication reunites the data. It's like having two pieces of a torn photograph. Each piece alone is ambiguous. Only when we put them together does the full image appear. Now let's place you inside the misconception. Imagine you're alone on a deep space probe, drifting far beyond the outer planets, where the sun is just a bright star. Back on Earth, a team has an entangled particle paired with one in your ship. You're told, if entanglement is faster than light, Earth can send you messages instantly. So you wait, you stare at your detector, you watch the outcomes, up, down, but they look like noise, random, meaningless. You can't tell if Earth is saying help or hello or we miss you, because Earth cannot steer your outcomes. They can't choose your pattern. and you can't decode a message from a stream that no one controls. If you want meaning, you must compare your results with Earth's results. And to compare them, you need a normal message, a message that still obeys light's speed. This is the quiet, devastating truth. Entanglement cannot be used as an instant radio, not because the universe forgot how to do it, because the universe refuses to let information outrun causality. Measurement in quantum mechanics is not like reading a number off a thermometer. It is an interaction, an event where a quantum system becomes entangled with a measuring device, with the environment, with the macroscopic world. That process produces an outcome we can record, and it produces a kind of irreversible mark, a classical fact. But that classical fact is local. It lives where the measurement happens. It does not broadcast itself across the universe at infinite speed. The correlations only show up when we later bring the records together. This is why quantum mechanics can be profoundly non-classical, without being a causality disaster. The non-classical part is in the structure of correlations. The causality-preserving part is in the limits of usable information transfer. We can say it plainly. Quantum mechanics allows non-local correlations, but it does not allow superluminal signaling. That's not an opinion, it's a structural feature of the theory, often summarized as the no-signaling principle. If we take two observers, far apart, sharing entangled particles, nothing one observer does locally can be used to force a specific outcome at the other observer's location, so no message can be sent. And because no message can be sent, no causal loop can be engineered, no paradox can be built. The universe permits strangeness, but it blocks catastrophe. It gives us a cosmos that is deeply counterintuitive, yet still consistent. Sometimes people ask, if entanglement links objects across distance, could it let us travel faster than light? But entanglement is not a tunnel through space. It's not a bridge you can walk across. It doesn't move matter. It doesn't move energy in a controllable way. It doesn't even move information in a usable way. What it moves is certainty, after the fact, once we compare notes. And comparison is always slower than light. So quantum mechanics doesn't give us a faster engine. It gives us a deeper description of reality's internal bookkeeping, a bookkeeping so precise that it preserves causality even while it violates our classical picture of separateness. So where does that leave us? It leaves us with a universe that has two personalities. On the surface, it is local, causal, and constrained by light speed. Underneath, it is woven with correlations that are not confined to classical notions of locality. But the speed limit remains untouched as a boundary for usable influence. Light speed still governs how fast cause can reach effect. Quantum entanglement doesn't overthrow that. It simply reveals that the universe is not built from independent pieces in the way our intuition demands. The cosmos is more interconnected than we expected, but not more permissive, not more chaotic, not paradox-friendly. And then the story tightens again, because if relativity protects the speed limit, and quantum mechanics also, preserves it, then light speed is starting to look less like a rule we discovered, and more like a rule reality is built around. But that creates a deeper question, one that doesn't care about laboratories, it cares about the entire cosmos. Why is this limit the same everywhere? Why is it identical in every direction, in every location, across billions of light years? Because if the speed limit is woven into space-time, then the next unsettling mystery is this. How do we know the universe has kept this rule uniform, from the earliest light we can see to the farthest galaxies fading beyond our horizon? There's a quiet assumption hiding beneath everything we do in physics, not just that light is fast, but that its speed is the same, everywhere, same in every direction, same from every galaxy, same yesterday, today, and in the oldest light we can possibly see. And if that sounds obvious, it only sounds obvious because the universe has trained us to trust it. But this trust is dangerous, because the moment that limit stops being universal, The moment it becomes a local habit instead of a cosmic law, reality becomes unstable in a way that's hard to even describe. Not because our equations would get messy, because the idea of an event would fracture, because before and after would stop agreeing with each other. And that's when the real question appears. How do we know the universe isn't cheating? How do we know the speed of light doesn't subtly drift as we move through space, as we look across billions of years, as we aim our telescopes into directions we've never touched? We don't get to assume universality. We have to interrogate it, and the only way to interrogate it is to look for places where it would leave fingerprints if it ever changed. Imagine this. Imagine every law of physics is written as ink on thin paper. Now imagine the universe is a windstorm, stretching that paper in every direction. If different regions of space were allowed to have different rules, that paper wouldn't just bend, it would tear. Because physics is not a collection of isolated facts. It's a network. Change one fundamental piece, and thousands of other things shift with it. So when we ask, is the speed of light the same everywhere? We're really asking something sharper. Is the universe one coherent system, or a patchwork? And scientists don't get to answer that with philosophy. They answer it with measurements, painfully careful ones. One of the first places to look is the most controlled environment we have here. Because if the speed of light were different depending on direction, even by a tiny amount, we should be able to detect it by building instruments that are sensitive to direction itself. This is the modern spirit of the Michelson-Morley idea, updated with lasers and resonant cavities. You build systems where light paces back and forth, and you watch whether the rhythm changes as the apparatus rotates with Earth. If space had a preferred direction, if there were an upwind and a downwind to the cosmos, the beat would shift. But it doesn't. Again and again, experiments push the limit lower, hunting for anisotropy, directional differences, and again, the universe stays silent. It's unsettling in a calm way, because it's not just saying light is fast, it's saying space itself is not allowed to pick favorites. But we can't stop at Earth. A laboratory is still one location. The real test is the sky, because the sky is time travel. When we look far away, we are not looking across distance only. We are looking back into eras when Earth didn't exist, when the sun was not yet formed, when life had not taken its first breath. And if the speed of light, or the deeper structure behind it, were different in those eras, we would expect distant physics to look wrong, not poetic wrong, mechanically wrong. Atoms would absorb and emit light at different patterns. Spectral lines, those sharp fingerprints of elements, would shift in ways that can't be blamed on motion alone. So astronomers do something almost haunting. They take light that left a distant quasar long before human history, passed through ancient clouds of gas, and arrived here carrying scars, absorption lines. Those scars are a record of how atoms behaved there and then. And for decades, teams using observatories like the ESO Very Large Telescope have used this method to test whether a key electromagnetic constant, the fine structure constant, has changed over cosmic time. The headline is simple. Across the observable universe, the measurements are consistent with no change within extremely tight limits. That doesn't mean the question is finished, because the measurements are hard, systematics are real, and the universe is cruel to precision. But it means something profound. When we interrogate the distant universe with the language of atoms, it answers back, in the same dialect. And then, something even stranger happened. We stopped relying on rare, perfect targets and began using crowds. Surveys like DESI, the Dark Energy Spectroscopic Instrument, collect spectra from enormous numbers of galaxies. And with enough data, you can look for tiny shifts in familiar emission line patterns across space and time. Not one object, not 10, hundreds of thousands. A map, a statistical interrogation of the cosmos. And what emerges is, again, the same message. No convincing evidence that these fundamental patterns drift across the surveyed universe within the sensitivity of the method. If the universe had regions with slightly altered electromagnetic rules, this is exactly the kind of net that should start catching them. So far, it hasn't. But that only deepens the mystery, because it means the universe is not merely consistent, it is coordinated. Now we take a step into something colder, not light, gravity. For a long time, people wondered, if gravity is geometry, if it's the shape of space-time, does it propagate instantly? Does it ignore the speed limit? And then, in 2017, the universe gave us a brutal gift, the event known as GW 170817. A pair of neutron stars collided, and we detected it in two ways: gravitational waves and light, gamma rays, arriving just about 1.7 seconds apart after travelling for an incomprehensible span of space. That time difference over that distance lets scientists constrain how different the speed of gravity can be from the speed of light, and the constraint is staggering. The speeds match to within a tiny fraction, so small it's almost hard to emotionally process. This is not a quiet lab test. This is the universe screaming across space with two messengers, and both arriving on nearly the same heartbeat. It's as if space-time itself is saying, no matter what force you choose, light, gravity, the speed limit is still written into the fabric. Because if the speed limit is truly universal, then it is not a property of light alone, it's a property of space-time, which means we are not free to imagine a universe where this limit varies casually, like weather. If it varied, even slightly in different regions, then the very structure that defines cause and effect would warp differently from place to place, and then we face consequences that aren't abstract. Here's one. If the rules of electromagnetism were different in a far region, atoms there would have different stability. Chemistry would not be chemistry the way we know it. Stars might burn differently. Fusion thresholds, spectral behavior, the cooling of gas clouds, entire evolutionary pathways for galaxies would shift. So the universality we measure is not just a nice symmetry, it's the difference between one coherent cosmos and a shattered one. And what makes this truly disturbing is that the universe appears to have chosen coherence. Not because it had to make us comfortable, but because coherence may be the only way complex structures survive long enough to matter. And now, place yourself inside the measurement. You are standing on a spinning planet, riding a moving solar system, drifting inside a galaxy that is itself in motion. Everything about your life is motion layered on motion. If the universe allowed direction to matter, if there were a hidden cosmic wind that made light slightly faster one way than another, then even your simplest act of seeing would become unreliable. Your eyes would still work, but the universe they reveal would not have a stable geometry behind it. Every sunrise would arrive on a slightly different clock, depending on Earth's direction through space. But it doesn't. We live inside a reality that refuses to let direction become destiny. So when we gather these threads, the lab tests that find no preferred direction, the distant spectra that keep matching our atomic rules, the gravitational waves that refuse to outrun light, the cosmic microwave background studied for statistical isotropy, we're cornered into a single idea, not an opinion, a structure. The speed limit behaves like a universal constant because the universe behaves like a single consistent space-time. And this does something subtle to the original mystery. It reframes it. The question isn't, why is light speed the limit here? The question becomes, why does the universe enforce the same limit everywhere, so relentlessly, that even across billions of years, the cosmos still agrees with itself? And that creates a bigger problem, because if the limit is universal, then it is not just restricting us, it is enabling something, a stable world, stable atoms, stable chemistry, stars that can burn in predictable ways long enough for planets to form. So the next question is unavoidable. If the universe is tuned to keep this limit the same, what does that tuning allow to exist? Because sometimes the most important part of a limit is not what it forbids, but what it makes possible. Out there, the night is not just dark, it is full of messages that have been traveling longer than any civilization has existed, arriving with a kind of quiet patience, carrying evidence that the universe is real and enormous and still unfolding. And every one of those messages obeys a single, relentless rule. Light moves at a fixed speed in a vacuum, 299,792,458 meters per second, about 300,000 kilometers per second, or 186,000 miles per second. We call it a speed, but that word is too small, because this number doesn't just describe how fast light travels, it sets the rhythm of reality. And here's the unsettling part. This limit, the very thing that feels like a restriction, is also one of the reasons anything stable exists at all. Atoms, chemistry, stars, galaxies, life. A universe without this limit wouldn't be more free, it would be more violent, more chaotic, more brief. So, we're not just looking at the speed limit, we're looking at what the speed limit allows and what it quietly prevents, every second, everywhere. Before we talk about atoms and stars, we have to admit something strange. We didn't merely measure the speed of light. We eventually built our measuring system around it. In modern science, the meter itself is defined using the fixed value of the speed of light. In other words, we treat this speed as so fundamental that we anchor human measurement to it. That should already make us uneasy. Because it means this isn't just a property of a thing called light. It's a structural constant, woven into how space and time behave. But it goes deeper than structure. This same constant is tied to how matter stores energy and how stars pay their bills. NASA explains the sun's power as nuclear fusion, hydrogen nuclei combining into helium with a small amount of mass converted into energy. That conversion is not a metaphor, it is literal. Matter contains energy so dense, so concentrated, that even a tiny mass difference can light a star for billions of years. And what sets the scale of that conversion? The same constant that caps speed in the universe. So when we say light speed is a limit, we also have to whisper the other truth. Light speed is part of the reason the universe can run slowly enough for structure to form, instead of detonating into pure immediate chaos. Now we step into the small, not small like dust, small like the place where the universe negotiates its most delicate contracts. Inside an atom, electrons are held by the electromagnetic force, the same force that produces light. And in physics, there is a dimensionless number that describes the strength of that electromagnetic interaction. It's called the fine structure constant. Its value is about 1 over 137. That number is quiet, but it is everywhere. It shapes how tightly electrons bind to atoms, how atoms absorb and emit light, and the fine details of atomic spectra, the fingerprints scientists use to identify elements across the cosmos. And here's why it matters for our story. This constant involves the speed of light. So buried inside the behavior of electrons, inside chemistry itself, is a relationship to that cosmic limit. It's as if the universe stamped the speed limit into the rules of matter. Most of the time, the speed of light feels distant, something for rockets and telescopes. But it is closer than breath, because electrons in atoms move, and in the simplest atom, hydrogen, the characteristic speed of the electron is a small fraction of light speed, tied directly to that 1 over 137 number. So for hydrogen, we're talking about around 1% of light speed. That alone is unsettling. Even in the calmest atom, electrons are not gently drifting like slow planets. They are fast. But the real shock arrives when we climb the periodic table. As elements get heavier, electrons are held more tightly, and the inner electrons move faster, so fast that relativistic effects become unavoidable. This is not science fiction. This is chemistry. The Royal Society of Chemistry discusses how relativity significantly affects heavy elements, changing their electron behavior and, as a result, changing their chemistry. And this is where the universe reveals something almost poetic. The speed limit doesn't just stop spaceships, it shapes the color of gold. Gold is not yellow by accident. In heavy atoms like gold, the electrons move fast enough that relativity shifts energy levels and affects which wavelengths are absorbed and reflected, altering the color we see. Mercury is not liquid at room temperature by coincidence either. Relativistic effects change how Mercury's electrons bond, weakening the bonding that would otherwise make it a solid metal. So when we talk about a universe tuned for limits, it's not an abstract claim. It's in your hands, it's in the periodic table, it's in the fact that chemistry has texture, variety, and stability, instead of collapsing into something unrecognizable. Imagine this. You're holding a gold ring under a lamp. It looks warm, almost like sunlight trapped in metal. But what you're really seeing is a tiny relativistic correction, not in a particle accelerator, but in jewelry, a whisper from the speed of light living inside matter. And that creates a bigger problem. If light speed is buried inside chemistry, then the limit isn't merely out there in space. It is inside the structures that make life chemically possible. We often say stable, like it means still. But stability in the universe is not stillness. It's a balance held under tension. Atoms are stable not because nothing is happening, but because the rules force a negotiation between attraction, motion, and quantum structure. The fine structure constant sets how strong electromagnetism is, and its measured value is one of the central parameters of atomic physics. In our universe, most atoms live in a regime where their everyday chemistry can be described without extreme relativistic chaos, but with enough relativistic influence in heavy elements to create richness, like the strange chemistry of gold and mercury. That is a balance, not too rigid, not too volatile, not too simple, not too broken, and it's tied quietly to the same constant that limits speed. But chemistry is only the first miracle, because atoms alone don't give us warmth, they don't give us sunlight, they don't build planets into habitable worlds. For that, we need stars, and stars are where the speed limit becomes something else entirely. A star is a furnace built from gravity. It crushes its own core until nuclear fusion can begin. NASA describes the sun's energy as coming from fusion in its core, hydrogen combining into helium, releasing energy. But here is the question that should haunt us. If a star releases energy by converting even a tiny fraction of its mass into radiation, why doesn't it explode instantly? Why doesn't it spend its entire budget in one catastrophic moment? One answer is deeply connected to the same cosmic rule. Energy and information do not propagate instantly. They are limited. Radiation pressure, heat flow, the transport of photons, everything must move through the star under constraints. And inside the sun, photons do not go straight out. They scatter, they bounce, they random walk. NASA and educational resources describe how energy generated in the sun's core takes a very long time, thousands of years, moving outward through the sun's interior before finally escaping as sunlight. That means the sunlight touching your skin today is the final chapter of a story that began long before modern history, before telescopes, before empires, before our written memory was even possible. This is the balance between change and stability made real, an engine powerful enough to shine, but slow enough not to annihilate itself. Picture this, a crowded hallway where no one can move in a straight line. You try to walk from one end to the other, but every step you take you bump into someone, turn, stumble, redirect. That's a photon inside the sun, energy trying to escape, slowed by constant collisions, forced into patience. And the speed limit is part of what makes this patience meaningful, not only because light itself has a maximum speed, but because the universe refuses instant outcomes. It forces processes, it forces delays, it forces time to exist as more than a backdrop. And that is why stars can be long-lived furnaces rather than brief flashes. Now step outward, from atoms to stars, from stars to galaxies. A galaxy is not just a collection of stars, it is a memory structure, a system where gravity shapes long-term stability, where stars are born and die, where heavy elements are forged and recycled into planets. And the speed of light sits behind the entire experience, because it limits how quickly anything can influence anything else. Even the simple act of seeing is delayed truth. When we look at the sky, we are not seeing now, we are seeing when the light left. And that delay is not an inconvenience. It is part of the universe's architecture, one that prevents everything from becoming instantaneous, everywhere, all at once. Life depends on gradients, not absolutes, on steady energy input, not sudden universal synchronization, on chemistry that can build complexity without being torn apart by immediate, unrestrained exchange. NASA's description of the sun's fusion-powered energy is, in a way, also a description of why life has time for climates, ecosystems, evolution, and memory to exist at all. We don't usually connect these dots. We talk about light, speed like it's a wall at the edge of science. But the truth is darker and more beautiful. The limit is not merely a boundary, it is a stabilizer, a kind of cosmic damping, preventing reality from becoming too fast for structure to hold. So what have we really discovered here? That the speed of light is not only about travel, it is part of the electromagnetic rules that shape atoms. It quietly reaches into chemistry, into the behavior of heavy elements like gold and mercury, where relativity becomes a chemical force, and it governs how stars can shine steadily, because energy does not escape the sun's interior in an instant. It crawls outward over immense timescales. In other words, the universe is not merely constrained, it is protected. Not protected for our comfort, protected for coherence, for continuity, for the slow construction of complexity. But then, a final discomfort remains. If this limit is stitched into matter, if it shapes the glow of stars and the stability of atoms, if it keeps the universe from collapsing into instant chaos, then what is light, really? Not as a thing, but as a messenger. Because every sight you have ever seen, every memory you have ever formed, arrived riding on that limit. And that raises another question. If the universe is tuned so that reality can only be revealed at this speed, what does that say about what it means to know anything at all? There is a kind of silence built into the universe, not the silence of empty space, not the silence between stars, a deeper silence, a rule, because no matter how violently the cosmos evolves, no matter how far we stretch our imaginations, there is one boundary that never flinches. Light moves at about 300,000 kilometers per second, about 186,000 miles per second. That's fast enough to circle Earth about 7.5 times in a single second. And yet, the strangest part is not that it's fast. The strangest part is that it's the same, everywhere, every when, and the universe treats that number like something sacred. Not because light is special in the way we usually mean, but because that speed is the edge of what can connect to what. It's the speed of cause meeting effect, the speed of before staying before, the speed of reality staying consistent. And once we understand that, we stop thinking of light speed as a wall, and we start seeing it as the framework that holds everything up. Here's how serious this limit is. The modern world doesn't just measure light speed, we build our measurements on top of it. Today, the meter, the very idea of 1 meter, is tied to how far light travels in a precise fraction of a second. The value of the speed of light is treated as exact in the SI system, and our units lock onto it like a compass needle snapping toward north. That is not a poetic detail. That is civilization admitting something quietly terrifying. We do not define light speed. Light speed defines us. And yet, even that still isn't the heart of it, because the deepest truth is not about rulers and clocks. It's about whether the universe can remain coherent at all. Imagine this. You're standing on a long, empty street at night. You clap your hands. You know the sound will take time to reach someone far away, so you can feel the delay. You can predict it. Now, replace sound with light. You flip a switch. A distant window lights up. In your mind, it's instant, but the universe doesn't allow instant. Not truly. Light is the messenger we rely on for everything we claim to know. It carries the shape of distant galaxies into our eyes. It carries the warning flare of a supernova across impossible darkness. It even carries the face of someone you love across a room. And the rule is simple. No message can arrive before it has time to travel. That sounds obvious, until we realize what it forbids. Because if anything at all, could carry information faster than light, then before and after would stop being stable, and the universe would begin to fracture. We often say, nothing can go faster than light, but that sentence hides the real meaning. The deeper statement is, nothing can carry cause and effect faster than light, because once signals can outrun light, reality loses the ability to agree on what happened first. In the logic of relativity, different observers can disagree on what events are simultaneous. And that matters, because it means faster than light signals can imply, in some frames, effects arriving before causes, exactly the kind of paradox the universe refuses to permit. So this speed is not just a number, it's an agreement the universe enforces, a guarantee that events can be stitched together into a single story, without tearing. And that's why this limit feels so absolute. Not because it's inconvenient, because without it, the cosmos can't keep its own timeline intact. Here is where many people instinctively reach for the wrong idea. We imagine light as the strongest traveler, the universe's ultimate sprinter. But light isn't fast because it tries harder. Light is fast because, in a deeper sense, it doesn't have the option to be slow. In modern physics, this limit belongs to space-time itself. It's the conversion rate between space and time, the maximum speed at which influences can propagate in a vacuum. The number shows up not as a preference but as structure. So when we say light speed, we're naming the speed of light, but we're also naming something more universal, the speed of any massless influence, the speed of connection, the speed at which the universe can update itself. Light just happens to be the most familiar messenger that obeys the rule perfectly. We hear 186,000 miles per second, and our mind goes blank. So let's force it back into human reality. At light speed, you could travel from New York to Los Angeles in about 1/100th of a second. You could go from Earth to the Moon in just over a second. And even then, the scale of the universe is so vast it turns light into a crawler. The center of our own galaxy is so far away that if a beam of light started its journey when our ancestors were painting on cave walls 26,000 years ago, it would only be arriving around now. This is what the limit does. It makes the universe legible, but never instant, reachable, but never trivial. And that slowness on cosmic scales is not a flaw, it's the price of causality. Now comes the part that can feel unsettling if we let it, because this limit doesn't only govern distant galaxies, it governs the room you're in right now. You have never seen anything in the present, in the pure sense. You have only seen what light has had time to bring you. When you look at a wall across the room, you're seeing a fraction of a second into the past. When you look at the moon, you're seeing the moon as it was a little more than a second ago. When you look at the sun, you're seeing a version of it from minutes ago. And when we look deep into space, we are not looking across distance, we are looking across time. A light year is literally a distance defined by how far light travels in 1 year, about 9.46 trillion kilometers, about 5.88 trillion miles. So every cosmic image is also a fossil. Every star field is a museum exhibit of old light. And the speed limit is what makes those exhibits possible, because it ensures a consistent order in which information can arrive. This is the reframing that changes everything. Light speed isn't the universe saying, "You may not go faster." It's the universe saying, "This is how space-time is stitched." If we could break that limit, we wouldn't just gain a new engine. We would gain the ability to rearrange the order of events, to let consequences leak ahead of causes, to let the universe contradict itself. And that is why the limit isn't negotiable. Not because we lack imagination, but because the universe is not built like a playground. It's built like a logic, a strict, calm, uncompromising logic. And the speed of light is one of its deepest grammar rules. And now, just for a moment, place yourself inside it. You're not merely watching the universe, you are receiving it. Every face you recognize, every memory you carry, every star you've ever admired, arrives to you only as fast as light can deliver it. Even your own reflection in a mirror is a message traveling out and back, a tiny round trip through space-time. The universe does not give us reality directly, it gives us reality through a courier, and that courier has a limit. So when we ask, why is light speed the ultimate limit? We're really asking, why does the universe have an edge to connection? And the answer is almost unnervingly simple, because light speed is not just the speed of light, it is the maximum speed at which time and space can coordinate. The maximum speed at which causes can safely produce effects. The maximum speed at which the universe can remain one coherent story instead of a shattered collage. Light is the messenger that binds events into meaning. And the quiet truth is this: the universe reveals itself to us no faster than it can be understood, not because it is hiding, but because the act of knowing requires a signal, and every signal must travel. So every sight, every moment, every memory arrives, carried by light. And in that limit, strangely, there is mercy, because without limits, nothing holds. Without limits, nothing lasts. And without this one, this calm, absolute speed, even reality would have no way to stay in order.